So when we find, in MHF we did this a little bit, and we talked about it a bit more, I would say, when we started looking at the new version of the function of the formula to find a derivative, the one with the h, right, as h approaches 0. And we saw that you can come up with an expression for the derivative or the slope of the tangent or whatever you're going to call it. Let's take a look at that. So if I go back to our last unit, well, there you go, right? So for this question, the original function was y equals the square root of x plus 4. And we found the derivative of that function to be 1 over 2 times the square root of x plus 4. Notice that that's the same. We're going to find out in the next unit a little bit more about some of the patterns that happen in finding those kinds of derivatives, a new way of doing it. But so we notice that the original function is in there. It's in the denominator now, and it's got a 2 out in front of it. But that's an expression for the slope of the tangent at any point, or that's the derivative function of the original function, right? Straightforward enough. But it's a function in and of itself. I mean, this is a function that we may have explored. It's a little bit like we didn't usually do rational and square root, but we probably saw that, in little activities here or there. So it's a function in and of itself. And every function has the same properties that we can talk about, characteristics that we can explore, like domain and range. Is it continuous? That sort of thing. And now we think about what we've learned in this unit, everything we've learned in this unit about continuity, about limits in general, about the relationship between limits and continuity. We're just going to explore that. It's pretty straightforward again, but we're going to explore that thinking just a little bit further. And maybe it kind of helps us see why we approach this unit the way we did, thinking about limits and continuity and then derivatives. The new formula for derivatives using h is, like I said on Friday, a common way, like that's a more common formula that we use for this stuff, but it's just kind of the calculus way we're going to do it. So whether you use this formula that you can see up here, x minus a on the bottom, or h, that's neither here nor there, but the point is relating derivatives and limits and continuity together is kind of what we're doing today. So imagine at some value, a in this case, whether it's 2 or negative 2 or 10 or whatever it is, so some particular value, okay, the limit of the function doesn't exist. Now, this is the derivative, so f prime is that original function in the difference quotient evaluated at a, right? Imagine it doesn't exist. What does that tell us about f prime or about the function itself? What do you think? Good. What does? The derivative function, f prime. Yeah, okay. What else? What does it tell us about the original function? Right? They're connected in some way. In some important way. So if we know something about the derivative of a function, what can we deduce about the original function? So what this is telling us, is the derivative doesn't exist. The derivative of f at x. If the limit of the function doesn't exist, the derivative doesn't exist. I suppose you could kind of go back and forth with that, right? Like, if the limit of the original function doesn't exist, then the derivative doesn't exist. Or if you know something about the derivative, if it doesn't exist, that's telling you something about the original function. Jason, yeah, you had your hand up. The original function? Yeah, that's a possibility. Is that the only possibility? What is another way, and I've said it already today, what's another way that we think of the derivative? What do we always call it, in particular in MHF? Emma? Slope of the tangent. So if the derivative doesn't exist, what does that tell us about the original function? Like, it's not for sure. We're not certain. I'll give you that hint. But it tells us something about the function. What does it tell us about the slope of the tangent to the function at that point? Yeah, it could be that it's a vertical line. It could be that the function itself doesn't exist or something like that as well. Like, there's other possibilities, but very good. It could be that the slope is undefined. There are a few other situations. It's kind of like an undefined slope, but it's also the function's doing something weird, and so what would it even mean to have a slope at that point? Kind of what undefined means. But good, very good. Okay, so one note that's sort of related to this, but just kind of like a definition or a notation thing. If the derivative does exist, then we say f at x is differentiable at a, or at x equals a. So f at x may or may not be differentiable in different places. You could find the derivative function of f at x, and it will and won't exist maybe in certain places. It might be a polynomial and just exist everywhere. It might not. The square root function that we saw has places where it definitely won't exist, right? Any questions about that? My butchering of the word does reminds me of a story that a professor told me in university. It was a philosophy of religion course. I think that's what it was. Or history of religion? Philosophy? It wasn't philosophy of religion. It was Eastern religions or something. It was like a first year course. It was sort of interesting. And he told this story. He was writing on the board, and he told this story how one time he was in the middle of class, and you have these moments where, like, I guess everybody does. When you're teaching, I think it happens when, like, you're writing something, but you're thinking about something else. Like, you're thinking about what's coming next, and you're not thinking about what you're actually writing, and you make, like, typos or that kind of thing. Anyway, and he was stuck on the word does, and he couldn't remember how to spell it. Like, all of a sudden, he had this moment where the word does didn't make any sense to him. And he's like, is it D-O-E-S or is it D-E-O-S? And he couldn't, like, for the life of him figure out. And he could only imagine that he's in front of, I don't know, he's in front of these, like, third or fourth year university students, and they're probably sitting there thinking, oh, he's trying to word this sentence in this awesome, like, eloquent way, or what's the perfect way of putting this, religious, mystical piece of information that he's coming up with. Meanwhile, he's trying to figure out how to spell the word does. Anyway, happens to everybody, right? Okay, so if the derivative does exist, it's differentiable. If it doesn't exist, this tells us something, and there's a relationship between a function and its derivative, absolutely. Here are some examples. Some of these are things that we've seen, and some of these are going to be kind of new. Some examples of a function or of functions. And that the important thing about this is these are functions that have a value at x equals a, but the derivative doesn't exist. So the slope of the tangent doesn't exist, or however you think about it, f prime does not exist. So the derivative does not exist. And this is important because if a function doesn't exist, then obviously its derivative will not exist at those points. But here are places where the function does exist, but the derivative does not. So first one is, we call them cusps, or you might think of it like a point. So points. So at a, so that looks like the absolute value function to me. So this function, here I'm going to make it blue. This function is f at x, and the derivative does not exist. Oh, sorry, of a, that should say a. Everywhere else it would exist, but not at a. In grade 11, I imagine when you first saw the absolute value function, you probably found it to be a lot like a parabola in your mind. It has a horizontal shift and a vertical shift. It's just a lot easier than a parabola because otherwise it's just two straight lines, right? The growth is really simple. So graphing them is pretty straightforward. You don't do much other than graph them, I think, in grade 11. But otherwise, it's very similar to a parabola. It opens upwards, opens downwards, that kind of thing. But it's different in a way that a parabola has a smooth transition from decreasing to increasing or vice versa. Whereas the absolute value halts immediately and changes direction. And so that's like a cusp or a point. It's changing direction on a point, not through a curve. So the absolute value, so for the absolute value function, the derivative doesn't exist. It makes a difference in the context of what you're talking about, yeah. This we're talking about at a particular point. So for this question at the top here, I have f at x equals some function, I can find the derivative of that function, that's no problem. At the point A, where I've marked the point as the point, right? Yeah. See what I'm saying? So that's the difference. So, and usually that's how we distinguish. Usually when we're talking about A, we're talking about at a particular point. And when we talk about X, we talk about anything. Okay, another way that you might see a cusp is like this. Here, I'll try to use blue again. So it's got curves, but it curves to a point and then curves back the other way. So if this point is A, then again, f prime at A, we're just going to keep writing this all the time, even though it's the same thing every time. F prime at A does not exist because that's a cusp. Whether there's arrows on the ends and it continues doesn't really matter, but imagine that it does. Imagine that the rest of the function is just perfectly normal. This function exists everywhere except for, or exists everywhere actually. It exists at A. Remember, these are all functions where the function exists at A, but the derivative doesn't. Everybody good? Kind of see where we're going with this? That was examples of cusps. A vertical tangent line. So the slope, goes back to what Emma said, is undefined. What if I drew something like this? Well, that's not a function. So that wouldn't really count. That's one that you've probably seen before. Maybe you would think of yourself something that is a function. Blue. Looks like a cubic, but it's lying on its side. And at that point, that would be like the vertex where it's actually doing the twist. It would have a vertical tangent line. I'm going to keep going. An end point. Why would an end point fit this definition? Right. So actually, I'm going to draw an example that's a bad example. I should come up with another one. Oh, I could. Let's do that. The example I was going to draw was, I'll do two. I was going to draw this. The square root function, that would kind of have an undefined slope anyway because it's like a parabola lying on its side. So maybe that's a bad example, like I said. But what if I did another one like this? Well, that's not a curve. How about like that? So normally, if it had a left side to the graph, that green part, so for both of these, it's going to be true. The problem is the strict definition of limit, the left-hand limit has to be equal to the right-hand limit. And this one wouldn't have a left-hand limit. Like Emma said, it doesn't matter which side you have, right? But this one would not have a left-hand limit. So you could draw a tangent line, but it doesn't fit the definition of a limit strictly. So in all honesty, it would kind of depend on the context of the problem you're trying to solve, I suppose. But strictly speaking, the limit doesn't exist. And so the derivative at that point does not exist. Max? No, doesn't matter. It's just that's the point, if I follow it down, where it does the twist. You know what I mean? Like I said, imagine that like a cubic that's been rotated. And that's something that you could probably easily come up with the equation for that. So this one's f at x, and this one's f at x. So we're not talking about the limit of this. We're talking about the function itself. F prime, the function, does not exist at a because it represents the limit of f at x at a. Does that make sense? Confusing going back and forth. And the other one is one that I think people have kind of been thinking of as a break. A break where it exists at that point. F prime at A does not exist. There's a few questions in the practice tonight that kind of ask about those examples specifically. So it's worth thinking about. I think the bigger picture lesson here is this idea that there's a relationship between the derivative function and the original function and where the derivative function exists and so forth, back and forth, right? Any questions? Yeah.
Okay, so you said that if the limit doesn't exist, then the derivative doesn't exist.
Mm-hmm.
What if
They might. Yeah. But the slope of the tangent doesn't exist at those points by definition. So that's part of what we're exploring here. I think I understand what you're saying. Like, so is the limit existing or not a perfect test to whether or not it will, and not necessarily there's other things that we need to know about these. Does that make sense? Yeah. So you may do the limit test and get an answer, but turns out that that's not going to be the answer to like every question. Does that make sense? Understand what I'm saying? Okay. All right, this one's going to be fairly straightforward. In fact, I'm going to let you just get started on that using the definition of a derivative. So the formula that involves h. Find f prime at x. So I'm going to ask you to go ahead and do that. Give you a few minutes to do that. And then we're going to talk about it. We're going to look at a couple of other properties today. If we don't quite get to all of it, we have about 10 minutes left. That's fine. We'll finish it up tomorrow. Not a big deal. And so what we're doing next is kind of unrelated to what we were just doing before, just as an FYI. So the limit as h approaches 0. Okay, go ahead and finish that one. If you had to pause and think about this for a moment, you can take a look up here at what we have. Remember, function notation allows me to just say whatever's in this bracket goes in for x. So if this is x plus 1 squared minus 3, now it's x plus h plus 1 squared minus 3, which means I have to expand that x plus h plus 1 times x plus h plus 1. And that's not something we often do, a trinomial times a trinomial. But it is. This is where, again, some of these ideas are simple, but calculus, the algebra does get a bit harder. Like that's not, this is something that you should be able to muddle through at least and get correct without a lot of struggle, ideally, for a course like this. One way you could think about it, and back in grade 9 when you started talking about distributive property and multiplying binomials, you may have seen this at some point, is I take the first term and multiply it by every term, and then the next term and multiply by every term, and then the next term and multiply. I mean, that is what's happening, but in your head, that might be a better way to do it. Like with binomials, we know the pattern in the habit. So x times all of those things is going to be x squared plus xh plus x, and then h times all those things is going to be plus xh plus h squared plus h, and then 1 times all of those things is just going to be x plus h plus 1. Kind of messy. So then minus 3. And again, be careful. I'm subtracting. See the big brackets that I have because I'm subtracting the entire function. And I've got little brackets inside. So minus x squared plus 2x plus 1 minus 3. Any questions about this so far? It's just algebra, but it's a bit messy. Okay, do you want to just watch? I'll do this for, you can do it yourself. Maybe you've already done it, but I can do this for everybody. We'll see what we get on the next step. So I'm just going to look through. I've got an x squared term here and an x squared term here. You kind of know after you do a bunch of these that a lot of things are going to add to 0, right? I've got 1 minus 1 and negative 3 minus negative 3. I have x plus h and x plus h, so 2 of those. I've got x here, and minus 2x here. What else do I have left? Think I've got it. So I've got h squared plus xh, so plus 2xh. And then, so xh, and then 2 h's plus 2h. Yep. I did that in my head. So like I looked and I said x squared minus x squared. They're gone. Yeah. To avoid writing out every one of those terms again just to multiply. But you could, absolutely. Or maybe you did it with that step. You could do it through. Okay. Factor out an h. So h plus 2x plus 2. Those are gone. Sub in 0 for h. And I've got my expression. So f prime of x is 2x plus 2, and f at x was x plus 1 all squared minus 3. The question we were given was this. F at x equals x plus 1 all squared minus 3. Okay. And we were supposed to find the general derivative. So I talked earlier about essential skills. We didn't actually formally do a summary. I just talked about it a little bit. But again, graphing a parabola, especially when it's in transformation form, is like an essential skill. This is not something that you should be stumbling with. And I only say that to mean if you are, like that's going to make everything that much harder. If you're struggling with this, it's harder to do all the other stuff. And that might be why you're struggling. So it's good to know that. Okay? So this is a shift to the left 1 and down 3, and otherwise it grows like a normal parabola. If I go over 1 and I square it, I go up 1. If I go over 2 and I square it, I go up 4. If I go over 3, I square that and I go up 9, right? So here's my points. 1, 2, 3. Nope, 1, 2, yep. And I don't know if I can fit 9 on there. Oh, I can. I don't think we need those, but put them on there anyway. It should be easy and it should be fast. Like if you have to spend 5 minutes thinking about how to graph a parabola, it's just going to take you that much longer to do everything. Okay, is that right? Think we're good? And we found, Emma, you don't look convinced. They're way too far up there. You are right. Thank you. 2, 3, 4. They should be right about there. That does look a lot better. Looked funny. That's amazing. I remember when I teach grade 10, I talk about that. Like after a few days of graphing parabolas, you get a sense of what it looks like. And that's what you're aiming for. And then some people graph their parabolas and they go like this at the end for some reason. You're like, oh my gosh, what are you doing? That's not a parabola. Anyway, good. Yes, that looks better. And then we found the derivative. Like I said, we did this yesterday. Remember, that's how we denote the derivative. And we found it to be 2x plus 2, I believe. Now I'm graphing a line, and my line has a y-intercept of 2 and a slope of 2. So I go down 2 over 1, down 2 over 1. It's sloping up to the right. It's hard for me to draw straight lines. I'm going to try. Oop. My best. How's that look? We talked about the relationship. I'm going to let you get caught up and make sure everybody's there, but so there's a relationship between a function and its derivative. I ask you, what's the relationship? It was a lot like this. Yeah, very good. Okay, so there in polynomials, there's a relationship in the degree of a polynomial function, its derivative. Exactly, very good. What else? From MHF, what is the derivative? What's another name for it? What is it giving us? What's it telling us? Slope of the tangent. So here's the tricky part, but once you get it, like it's not overly complex. There's just a few sides to it. You got to think about functions and function values and have a good grasp of like function notation or that sort of thing to really get this. If I pick a point on the original function, so how about I pick this point? X equals 1. What is the slope of the tangent at that point? How'd you get that? You said it right there. At x equals 1, the value of the derivative function, or the y value, is the slope of the tangent of the original function. That's the relationship. This is huge, right? Again, maybe a simple idea, but this is a big thing. If I think, and remember, we started yesterday by thinking how the derivative is a function in and of itself. The derivative is its own function. This one happens to be linear. It's a graph that you might have graphed in grade 9 academic math class and not known it was the derivative of something else, right? But you would have just graphed it. It's a function. It's a line. But this function, the y values of this function, tell us about the slope of the tangent at the same x value of the original function. See what I'm saying here? Everybody get that? A couple of people are nodding their heads. Some people are writing. Maybe you're writing it down. Maybe you're... I want to move on until I make sure people get that. So again, here we have a little demo here that we can look at. So the red line is the derivative function. It's 2x plus 2. It's the same one. The green line is the same parabola. And look at... I'm going to start over here. So here's my point. And you can see the tangent is this black line. Okay? And the tangent is quite steep. And it's negative. And look at the y value is down here. So it's almost -6. If I go up a bit more, it's going to be -6. Whoops. Okay, and as I'm coming down, the tangent's getting less steep, and the y value is getting bigger, like less negative. Okay, and right here at this point, the slope of the tangent is about 2. That's actually the slope of the tangent right there, that number is about 2. And the value, the y value on the red line is about -2. So the slope is -2 and -2. And then what happens here? Look what's happening. See, this to me really highlights the relationship and something's going on here, right? And turns out this is a big idea, something we'll cover a lot in the future in this course as well. Anybody want to try to articulate what's happening here? Jason?
As the tangent becomes positive slope, the actual line f prime at x is becoming positive.
Yeah, so the x-intercept of the derivative is occurring where the slope of the tangent changes from negative to positive. And you can start to think, you don't need to know this for this unit for sure, but you can start to think about what would cause the slope of a tangent to be changing from negative to positive on a function, right? And so then same thing as I go up now the slope of the tangent is 2, and the derivative function y value is 2. And again, these are always at the same x value. Okay, so this is a relationship that we're exploring and we're starting to get. Any questions about that? So you could show that in lots of other places. Let's do one more. Oh, so I could do a slope of the tangent. There's a question in the homework. Ooh, that was terrible. There's a question in the homework that was asking you to draw in tangent lines at points and then like sort of show and calculate their value using the derivative, that kind of thing, right? Like there was a question, I think, in the homework that was asking you to do that sort of thing. Okay, so there's one. I might pick another one here. And then if I follow that down, I can find the actual slope if I look at the associated y value in the derivative function. In grade 9, when you start exploring functions, you don't call them functions, but you start exploring relationships. What do? Like, what's the thing you learn about relationships, linear relationships in grade 9? The main thing. Anybody want to guess? You know this. We just used it to graph. John? Very good. To me, that's it. Yep, slope and y-intercept. What are those? They're properties of the function. What are we doing now with this calculus work and finding derivatives? We're finding more properties of the function. It's just more information so we know more about what it's like. And we can solve more interesting problems. And you saw in MHF, some of the problems we can solve is like, it could represent the instantaneous rate of change, instantaneous speed or velocity of your car, right? Could be calculated using this stuff. So it's just giving us more information about what's happening, what the function is like. So this is just, we've kind of already talked about this. Let's do it quickly. You can write all this down, or you can write it down later. You can get it later, or if you can just remember it, it's probably not super important to write this whole thing down. So this is for polynomial functions only. You got to know that. There are patterns and reasons why. There are patterns for all different kinds of functions. But for other functions, there'll be different kinds of patterns. But if you're given a polynomial function f at x and its degree is n, some value n, then f prime at x will also be a polynomial function, by the way. The derivative of a polynomial function will be a polynomial function, and will have degree n minus 1. So as Emma was talking about, Emma and Maddie noticed in the homework that the degree is always 1 less. So if I had a a quintic polynomial function, degree 5, the derivative would be degree 4. And you could take derivatives of derivatives. It's called the second derivative. Ooh, creative name. And you would then be at degree 3, and you could take the third derivative, and you'd be at degree 2. Like, you could keep going, right? And keep going down. So f at x is cubic, which means degree 3. This is all we're saying here. F prime at x will be quadratic, which means degree 2. If f at x is quadratic, so degree 2, f prime will be, what's it called? Linear. Degree 1. If f at x is linear, so degree 1, f prime will be, okay, I'll forgive you for not knowing the name of this one. What's the degree? 0. Anybody want to guess the name? Jason, you had your hand up. The slope wall. Nice idea. The slope of the line. Is that what you mean? It will be a horizontal line. And it will be the slope. Constant is the word we were looking for there. It'll be a constant. A constant is degree 0. In fact, didn't we see a question like this where there was like it was f at x equals 10, and I can't remember what the question was, but there was something in a lesson and it really confused everybody, but it was like a function can be f at x equals 10. That can be a function, and it's just a constant. It's a horizontal line, right? That's just, there's nothing wrong with that. It's not very interesting, but. And then if f at x is constant, so degree 0, f prime will be equal to 0, which has no degree. We don't really talk about the constant of 0 having a degree. This is not an important detail for right now, at least, but you could take the derivative of a constant and you would get 0. We don't have to know how to do that yet. Any questions about that? We will explore a lot more on derivatives of polynomial functions coming soon. Which of the following are polynomial functions? Do you think the first one is? What makes something a polynomial function? What doesn't? We did talk about this in MHF, absolutely. Maybe not a ton, but we do talk about like the names of different functions. So some of them are polynomials, some of them are rational functions. We have trigonometric functions, logarithmic functions, exponential functions. Those are at least some of the different kinds of ones we looked at. And polynomial functions take a particular form. Algebraically, they look a particular way. Their graphs look a particular way. They have particular properties. As I said, their domain for every polynomial is x is an element of the real numbers. And now we know something about the derivative of polynomial functions. So it's important to know and be able to recognize if something you're looking at is a polynomial function. Anybody want to guess for the first one? You can look back at your MHF notes if you can't remember exactly the definition of a polynomial function. At least I think we wrote it down if you were in my group. Nobody wants to guess? We should do a vote or something, but I think we're going to just try to whip through this. How could I rewrite this? What is x to the negative 2? Again, negative exponents are one of those things that we want to be able to do very well, not have it trip us up. We'll work on them a little bit in the next unit, so you'll get a bit warmed up with them. You haven't seen them, but that's something, you know, when you first see negative exponents in grade 11, a lot of people just do it wrong, kind of the whole unit. That's not going to be okay for us, right, in calculus. But 1 over x squared. So this is not a polynomial function. I'm going to put a big X. Nope. Because polynomial functions have to have positive whole number exponents. So you can't have a rational exponent either. Am I giving something up? Yeah, I just gave up an answer. Whoops. We'll talk about that when we get there. Okay, so the first one is not a polynomial function. Is the second one a polynomial function? F of x equals 17. What do you think? Yep, sure is. Red for bad, green for good. So constants count as polynomial functions. It's degree 0. We just talked about that. When we're talking degree, we're talking polynomial functions. In a rational function, you could talk about the degree of the numerator and the degree of the denominator, right? Because those parts are often polynomial. But we don't talk about the degree overall of a rational function. Third one, 3 to the x minus 4. What do you think? What kind of function is this? John? Exponential? Oh gosh. It's not even Monday morning. What's going on? Are exponentials polynomial? No, you can't have x in the exponent. The exponent has to be a number. X to the 1/2 plus 7. How could I rewrite this? Thank you. Square root of x plus 7. Square root functions are not polynomial functions. So that's what I mean by rational exponent. You can have fractions in the exponent. You can have negatives in the exponent. The exponent can be 0. The exponent on the x can be 0. That's a constant. That's degree 0. So f of x equals 17 is a degree 0 constant exponent on the x, 17x to the 0, right? We could think of it that way. That's fine. But it can't be negative and it can't be a fraction. What about the next one? Anybody want to guess this one? What part of it is rational? Oh, rational overall, yes. I see. Compare it to the next one. How are they the same? How are they different? I mean, you look like you might have changed your mind. What do you think? Yeah. So there's something to that. How could I rewrite this one? 1 over 4 x squared plus 3x plus 5. See, again, this is something that you don't see very often, so we get tripped up, but we want to start noticing those things. It's going to really help you if you start noticing those things. And I could expand that through, and don't you agree that polynomial functions can have rational coefficients? Nothing wrong with that. So this one is definitely polynomial. And this last one, as you said, is rational. It's got x on top and x on bottom. You can't have that. X on bottom is like x to the negative 1. Can't have that, so that one's not. So those are mostly examples of things that are not, a couple of examples that are hiding that you might not have thought. There's a homework, same homework as yesterday. Any questions?